My name is Melvin Friedman. Uh, I am retired from the government after 48 years of service. I'm currently an academic affiliate at George Mason University. I would like to acknowledge the help of my colleague, Brian Mark. This work was done in collaboration with him. We typically spend 1 hour a week for a period of a year, and this talk and other work are the result of those conversations. Now I'll go on to my next slide. The fundamental problem we considered is this: is it possible to design a road, traffic control system, and road to traveler feedback system that simultaneously satisfies these properties? A motorist traveling at a recommended constant average speed in any one of 4 orthogonal directions makes every traffic light in their chosen direction, regardless of their starting point or how far they travel in the chosen direction. Although I'm not going to cover it in this presentation, the same is also true for pedestrians and bicyclists. Another part of the fundamental problem is we require that the system have maximum potential flow. We also require that the system be capable of adapting to meet changing traffic demand. Now, an interesting question then is, does the problem have a solution? Even if one forgets about the bicyclists and pedestrians, it is not clear that the stated problem has a solution. The problem, however, does have a solution for motorists, bicyclists, and pedestrians. Here, we're going to focus on motorists. The concepts of designed road system, red C, green waves, and green arrows really help to solve the fundamental problem. So now I'll talk about some of those things. There are 3 road systems that we're considering: a Cartesian grid of alternate one-way roads, a Cartesian grid of two-way roads, and a Cartesian grid with a combination of 1- and 2-way roads. You might not be familiar what a grid of alternate one-way roads are, and that's illustrated in this figure. Here you see streets go alternately west, east, west, east, and they alternately go north, south, north, and south. So that's what we mean by a Cartesian grid of alternate one-way roads. For this system of roads, the gray squares are nominally a half a mile on a side, and not shown in the diagram are minor streets. And if these are half a mile on a side, that means there are several streets going north and south and east and west in each of these gray squares. I'll now show you what we mean by a Cartesian grid of two-way roads. Here you can see there are two-way roads because there's traffic heading west, east on the same road, and there's traffic heading north and south on the same road. And that's true of every road in the system. Here, the gray squares are nominally 1 mile on the side, and minor streets within the gray squares are not shown. The third class of road that we'll consider is this. Here we have a Cartesian grid of 1- and 2-way roads. Once again, these gray squares are nominally 1 mile on the side. And here you see we have traffic heading north and south on the same street, and we have traffic heading east and west on the same street. However, here I've designated 2 streets where traffic is only heading west, this one and this one. So that this is what we call a mixed a mixed road system. I've now defined the road system that I'm considering. Now I'm going to define what I mean by a red sea. But there are actually two kinds of red seas. One is a digital red sea, in which you imagine all the traffic lights in a city and in the surrounding suburbs are red in all four orthogonal directions. That's the digital red sea. The continuous red sea is a conceptual thing that helps you relate better to how the digital red sea works. You can imagine red lights are samples on the red sea. And in a continuous red sea, there would be traffic lights everywhere on the arterial roads. That's the continuous red sea. The utility of the red sea concept is that it allows one to think in terms of green waves, since the red light state is actually determined by the green waves. And so now I need to tell you what the green waves are and what their properties are. So imagine green waves traveling on the continuous red sea in actually four orthogonal directions: north, south, east, and west. Those are just, they're not necessarily the geometric north, south, east, and west. They actually correspond just to four orthogonal directions that we arbitrarily call north, south, east, and west. Then vehicles, like surfers, wait for a green wave to come by, and then they ride them to shore. However, in our case, the green waves never stop moving, which means that vehicles who ride the green wave never stop for a traffic light. We also have to demand that the waves never intersect one another. That's an essential requirement, and what it does is it avoids vehicle collisions. Because we want our system to be a maximum potential flow system, we demand that green waves have the property that when one wave leaves an intersection, another green wave in the orthogonal direction enters the intersection. And as you can imagine, this property ensures maximum potential flow at each intersection. We require green waves move with the same speed in the two orthogonal directions. This requirement is reasonable since the hypothetical road network is isotropic. However, this requirement is imposed for analytical convenience. And when we apply our theory to real cities, which I'm not going to do in this talk, then the fact that we will relax the requirement that vehicles travel at the same speed in the two directions. Now, what is the motorist's objective? The motorist's goal is to catch a green wave and ride it as long as the motorist travels on a particular road. The motorist who changes to an orthogonal road tries to catch a green wave on that road before being stopped by a traffic light. And the motorist may or may not be successful when he changes roads. The continuous red sea, in a continuous red sea, a motorist is stopped by a red light the moment a motorist is outside the green wave. In the real situation where you have a digital red sea, the motorist is stopped if he's outside a green wave when the motorist first encounters a traffic light. Okay, so now we introduce the idea of green waves in the fundamental problem. So if you can find green waves that satisfy green wave properties, you will have solved the fundamental problem. And you can wonder, do any green waves with the specified properties exist? The short answer is yes. The longer answer is the length of the green waves have discrete values to satisfy nonstop and maximum flow rate requirements. In a subsequent paper, Dr. Mark and I will are planning a paper called Introduction to Green Wave Theory. Now, there's also a need for green arrows. And you may say, why do you need green arrows? Well, traffic lights on existing roads have a short period when the traffic light is red in two orthogonal directions. The traffic lights, of course, also have an amber interval. These features are not captured in the green wave concept, but are captured in the green arrow concept. So what is the green arrow concept? The green arrows are basically a generalization of the green wave concept. As a generalization, they move at the same speed as green waves, and they're a useful concept for traffic light control. And what we envision is that the movement of green arrows on the Red Sea controls traffic light behavior. So when the tip of a green arrow enters an intersection, it turns the light green. Although it's not shown in our diagrams, we can imagine that the tail of the green arrows have amber tail feathers, and the shaft after the tail feathers is red. So when the tail feathers pass through an intersection, they turn the traffic light amber. And when the shaft after the tail feathers enters an intersection, it turns the traffic light red. Now, there's another concept that we need for all this to work, and that's a road to traveler feedback device. And the purpose of the road to traveler feedback device is that it informs motorists how fast the green wave is moving and where the traveler is relative to the green arrow. So this, for example, over here, this black spot here represents the particular vehicle that you're in. And here is the green wave you're riding in. This says that it's going at 35 miles per hour. And as long as you stay in this green rectangle, you're guaranteed to make all the lights. With this background, you're ready. I'm now going to convince you that it is possible to coordinate traffic lights with maximum potential flow so that you can make every traffic light if you go with the recommended speed. And here's an illustration of how that works on a city. Remember, these blocks are half a mile in size. So this is a city that's roughly 3 miles by 3 miles, since there are 6 blocks along the horizontal and 6 along the vertical. And you'll notice that at any given intersection, for example, if we look here, the moment a green arrow leaves an intersection, another green arrow enters the intersection. And that means if these green arrows are completely full of vehicles, then this network will have the maximum possible flow you can have. Now, you'll also notice that what I've done is here I've coordinated traffic lights on a system of alternate one-way streets. And you may wonder, well, is it possible to do this on two-way streets? And my next presentation will show you that it's possible to do it on two-way streets. So here are two-way streets, and you can see the vehicles are going in both directions on the street. And you'll also notice that each intersection is utilized fully, since whenever a green arrow leaves any particular intersection, another green arrow enters it. So that if these green arrows were full of vehicles, if there were a lot of vehicles traveling with each green arrow, this would have the maximum potential flow possible. However, in the 2 presentations that I've given you up to now, I assumed that there was an equal demand for flow in the north, south, east, and west direction. So these diagrams show equal flow in all four orthogonal directions. And the next demonstration will show you that you can still achieve maximum uninterrupted flow with a system of anisotropic vehicles. So I'll start the demonstration going, and I'll slow it down so that you can see how it goes. I'll also show that it works for a city of arbitrary size. See, n over here determines how large the city is. So I can make the city larger and start the presentation again. And you may be interested, the alpha actually controls the width of the streets. So if I increase, see, I'm making the streets wider now as I click on that. So my animation allows for variable width streets and also an arbitrary number of blocks. And you see that this is anisotropic flow because the arrows in the east and western direction are much longer than the ones in the north-south direction. And essentially what that means is that the lights are green in the east-west direction for a longer period of time than they are in the north-south direction. Now, what I've done here is I've shown that you can have maximum anisotropic flow on a system of alternate one-way streets. And you may be wondering, is it possible for me to achieve this on a system of two-way roads? And the next demonstration will show that it's possible to do this on a system of two-way roads. So here you can see there are two-way roads with the north-south arrows being short and the east-west arrows being long. And now I'll start the animation. And I'll slow it down so that it goes more smoothly. I'll speed it up a little bit. So you see that the animation can go at any speed. And this property, you can basically adjust the speed with which the green arrows move. You can adjust that to the density of vehicles on the road. And so what I've shown you up to this point is that I can satisfy the fundamental question. I show that the answer has a positive solution for alternate one-way roads, two-way roads, for isotropic flow, and for anisotropic flow. But the last two anisotropic flows had equal flow in the east-west direction and equal flow in the north-south direction. And you may wonder if you can make it even more anisotropic than that. Can you make it so that there's a greater flow toward the city in the morning and away from the city in the evening and still maintain uninterrupted maximum flow? And the next demonstration will show that that too is possible. So I've just executed this, and here you see we have a road. Basically we have two-way roads. Here's a road heading north and south, and here's a road heading east and west. But here's a road that's only heading west, and here's a road that's only heading west. And now I'll get that animation going. And I'm going to slow it down a little bit. And once again, you see it's a maximum flow network in the sense that as soon as one green arrow leaves an intersection, another green arrow enters the intersection. You can also see, though, that it's not isotropic. Because of this road and this road, there's considerably more traffic heading in the western direction than there is in the eastern direction. And actually, I stopped this, but you have seen that this arrow makes all of the, it never intersects any of the east or west going arrows. So I can replace this arrow by, I can replace this arrow with one that moves with this one. And that way I would have enhanced traffic. I would have enhanced traffic with 2 streets heading west and one street heading exclusively north. And so you see, I have very, very good control over the nature of the anisotropic flow. And I can adjust the anisotropic flow. I can adjust it to the demand that the drivers want. So if more drivers want to head north, but more drivers want to head east, I can do that. Okay, now I'll go on to the next slide. I gave you a brief overview of the road to traveler feedback device. Now I'll go into it a little more detail. Why do you need the device? Well, the green arrow speed depends on the time of the day. In existing cities, green arrows move at a variable speed because of uneven block spacing. So if you keep the traffic timing the same, you can compensate for the fact that some blocks are longer by having the green arrow speed up on those blocks. Another reason the green arrow speed changes is because in the morning and in the evening during rush hour, the density of cars on the road is rather high. And for that reason, the green arrows have to slow down because without much space between your vehicle and the one in front of you, you just can't travel as fast. And I have already shown you that the green arrows can speed up or slow down regardless, as needed. And so you need a way to tell the motorist how quickly the green arrows are going. And so the people who can use the road to traveler feedback device are motorists, bicyclists, and pedestrians. And with few exceptions, the device allows travelers to make every light. Now I'll show you what the road to traveler device appears like. So I've already explained, this is the vehicle. This red line over here indicates that motorists are not permitted to make a left turn during rush hour. These dotted red lines over here, not drawn quite to scale, indicate to the motorist that when these dashed red lines are in an intersection, pedestrians will have a chance to cross the street going from here to here, or from there to there. And so a motorist who wants to make a right turn and wants to avoid pedestrian walk signal would then try and position himself so that he's between the 2 sets of dashed red lines. This indicates that the green arrow is moving at 35 miles per hour, so that if a motorist was outside of the green wave, he could do either one of 2 things. He could speed up to catch the green wave ahead of him to make all the traffic lights, or if he was over here, he might slow down so that he's at the beginning of the next green wave. And when the device is fully zoomed, it shows what the cross street will be. And the device input requirements, essentially, well, I'll do it in detail. I'm running out of time, but when the device is turned on, it asks the user if the input data has changed since the device was last used. So basically, when you turn the device on, it wants to know if you're a motorist, bicyclist, or pedestrian. And if it hasn't changed, you just press enter. If you're a motorist, it'll ask you what your destination is. And if you want to give your destination, you give it by verbal command. And if you don't want to give your destination, you just press enter. The purpose in giving your destination is that if there's an accident or some traffic jam on the particular road you're on, then the device can alert you that you should switch roads and which road you should switch to avoid the traffic jam. It also asks you your maximum comfortable speed, the default being the speed limit, and you can press enter if you want to use the default. It will also ask you to state your lower maximum driving speed, which the default value is something like 15 or 20 miles per hour. And this tells the device how fast and how slow you're willing to drive to avoid being stopped by a traffic light. And the same thing is true for bicyclists and pedestrians. And with that input, the device can output, I'll give the device output. The device output gives you the speed of the green wave, and it tells the position of the traveler it tells you where you are relative to the green wave, so that you'll know whether to go to speed up, to slow down, or what you should do to make the green light. Yeah, so now I'll go on to the next. This can be used in existing cities, but in existing cities, because existing cities don't have the road system that I have presented here, you won't make every traffic light, and you can no longer go with a constant average speed. Your average speed will have to vary between traffic lights. And essentially what will happen when you apply it to an existing city is that you'll have regions of the city where motorists can make every traffic light, but as you travel from region to region, you will be stopped by a traffic light. This analysis I've done up to here assumed ideal drivers, and ideal drivers are one who try to get in and travel with the green wave. Analysis shows that non-ideal drivers will not be a long-term problem. Finally, I come to my conclusions, and I wanted to say Mathematica greatly facilitated discovering results and communicating results to others. The animations and videos used in this presentation were made with Mathematica, and all the diagrams in this presentation were made with Mathematica. And now I will entertain questions. Okay, John asked a question. How does the system adjust for traffic lights on major roads which are triggered only by demand, e.g. a car pulling out of a subdivision, housing road? I'll try and answer that. When a car tries to go on a major road, if the major road is not heavily trafficked, then the person coming out of the intersection will trigger a green light in the cross direction. What I have done is I've shown the analysis during peak hours, and during peak hours, that is during rush hour, because I was oriented toward having this work during rush hour, so people during rush hour could get home quickly. So during rush hour, they would get a green light when it was their turn for a green light. That is, when a green wave went by, they would have a green light so that they could go, and their arriving at an intersection would not trigger a light. Off hours, the green wave on the Red Sea method is not needed because the green wave on the Red Sea is meant to give uninterrupted maximum flow. And late at night, when there's not much demand on the main arterial, a car coming out of a subdivision would trigger a green light for it, just as it normally does. Let me see if there are any other questions. I need to refresh this. Okay, I don't see any other questions. Or maybe, okay, I guess that ends my talk. I'd like to thank you for attending, and I hope you enjoy the rest of your afternoon.